as far as temperature goes, there's a concept you kind of need to understand before we get to this statement down here. The concept is that even if you have a substance that is not moving, at the subatomic level, they are. So even baseballs, bow ties, bean bags, and bubblegum wrappers, even though if you were to set them on a table, they would all appear to be still. But they are not. At the subatomic level, they are moving. The molecules, the atoms, are actually vibrating. Now, that vibration has something to do with temperature. Take a look at this. Temperature is proportional to the movement in an object. So if we take this bazooka bubblegum wrapper and put it in the freezer, fewer of the molecules would be moving. You'd have less movement, I guess, by all the molecules. But if you were to put it outside in 90-degree weather, then you would have more of the molecules that would be moving. And you can kind of see this depiction here. We have the colder ones, you can't tell, but they're not moving as much as the hot molecules are here. And it can go back and forth. For example, you take the baseball, and if you put the baseball on ice, then the molecules are going to move less. And then you take the baseball and put it close to the fire where it heats up a lot, then the molecules are going to move more. Now, we can't have a very good judge of how fast things are moving at the molecular level. It's just too small. But fortunately, most objects expand with an increase in temperature. This bubblegum wrapper, if you were to set it out in 90-degree heat, yes, it would expand just a little bit. So that's the concept that helps us with thermometers. Ordinary thermometers are definitely based on this principle. The liquid mercury, or in some cases colored alcohol, expands and rises with the heat. The container is so small here that the hotter it gets, the liquid has no choice but to go up the container, or up this very small container, when it gets hot. So when it gets cold, it goes back down the very small container. It expands whenever it gets hot. But that's only going to help us so much, because there's a time at which this liquid in here would freeze if it got too cold, and if it got too hot, this liquid in here would boil over. So here's another concept. What do you do if you need a temperature or a thermometer inside a freezer? Well, here's what you do. Somebody cleverly came up with this a long time ago. If you put two metals together, you can see metal 1 here is on the top and metal 2 is here on the bottom, and you make sure those metals have different rates at which they contract and expand, that gives you what's called a bimetallic strip. Now, the ones that are used in some thermometers, usually it's like iron and copper, and they have different rates of expansion and of contraction. So when you have this bimetallic strip here, what happens is the colder it gets, one of them will contract, like this metal 2 is contracting, at the same time this metal 1 is expanding. If it were to get, colder, if it were to get hotter, this metal would be contracting and this metal would be expanding. So somebody a long time ago figured out if you can fix this bimetallic strip on an end and put it in a curl and get a pointer with it, if it were to have a rise in temperature, if it were to get hotter, they have the correct one on the outside that would expand. And by expanding, it would move this pointer toward the hotter degrees. And whenever it contracted, it would move this pointer toward the colder amount of degrees. And I thought that's very clever. And that way, since you have metal here, you don't have to worry about your mercury or colored alcohol freezing over. Now, we're not going to spend much time on digital thermometers because it involves a concept you haven't learned yet. A digital thermometer is completely a different story. There's going to be what you study later in this class called a direct current. And the direct current of ions flowing, just kind of bear with me right now, the direct current is going to change, and that's what's going to cause the temperature changes on the screen here. But don't worry too much about that just yet. Just know that that's what is coming. So, there are three major ways of telling temperature. We have the Fahrenheit scale, which we predominantly use. The Celsius scale is the SI unit, however, for temperature. So there are many times where you'll need to change Fahrenheit into Celsius whenever you're using SI units. Now there is another thing called Kelvin. So Fahrenheit, Celsius, and Kelvin are the three ways in which you can gauge a temperature. Fahrenheit and Celsius have a similar equation because you have in one case 9 over 5 and then you have its inverse 5 over 9. But Kelvin's a whole different ballgame. Kelvin is Celsius plus 273. Why 273? Because scientists have calculated that subatomic particles in an object actually have no movement at negative 273 degrees. You know how I mentioned, I think we mentioned it with the baseball back here, that this baseball has objects moving in it. The subatomic particles are moving. But if you were to take this baseball and take it to negative 273 degrees, that's where scientists think those particles actually stop, or at least get so little movement that they can't measure it. So that's why 273 degrees. The particles have stopped at 273 degrees for our purposes. So you cannot have a Kelvin reading below zero, because according to scientists, you cannot really measure anything at 273 degrees below zero. And I mentioned 273 degrees below zero. It's 273 degrees Celsius below zero. So it's just really not able to record that very well. You might hear some kind of estimation like that that would be below that, but they really can't tell below that. So that's why Kelvin measurements, there's no such thing as a Kelvin measurement. Okay, why don't we do some calculations here. I'll get this with pen and put it on purple. Okay, if we have 40 degrees Celsius, how are we going to get that to Fahrenheit? So let's see, we'll write the formula first. Fahrenheit equals Celsius, which is going to be 40 degrees, times 9/5 plus 32. So let's take care of this part first. 40 times 9 equals 360, if you were to put that in your calculator, divided by 5, and then have that plus 32 degrees. So let me go to my calculator, see that, what is that, 360 divided by 5? 360 divided by 5 equals 72. So that means we have, this part is 72, so it would make it 72 plus 32. 72 plus 32, of course, looks like it is 104, so we're finding Fahrenheit, so that is 104 degrees Fahrenheit. Why don't we try moving from Fahrenheit over to Celsius? So Fahrenheit to Celsius, let's use this formula. Celsius equals, let's see, that would be 80 plugged in there, 80 minus 32, and then after that you'd have times 5/9. So 80 minus 32, that would be what, 48? And multiply that times 5 over 9. So I would multiply 48 times 5 first. Let's see what that would be. 48 times 5 equals 240. That's what that looks like. So that would be 240 over 9. So 240 over 9, oh, already got 240 here, divided by 9 equals 27 degrees. Notice I'm rounding up from 26.66. So that would be 27 degrees, and we are looking for Celsius. So it would be 27 degrees Celsius. Okay, let's do one in Kelvin. We have 300 degrees Kelvin. Why don't we find Celsius? So we're going to have to take our formula. Kelvin equals Celsius minus 200 or plus 273. So I'm going to add 270 or take away 273 to both sides, and take away 273 to that side. Those would cancel out, so I'm going to move Celsius to this side. Celsius equals K minus 273. So K in this case will be 300, and 300 minus 273 sure looks like that would be 27 degrees Celsius. It's ironic I had the same answer here. I want to take this 27 degrees to Fahrenheit, and that actually will be pretty easy considering you've already done this problem, but let's just at least set it up. So we'll have Celsius here, and that would be Fahrenheit equals 27 degrees, talking about this formula right up here, times 9 over 5 plus 32, and that's how you'd end up finding, and I know it'll come out to be 80 degrees Fahrenheit because of the numbers there. So hopefully you can learn, hopefully that gives you at least a start on how to do those. Let's talk about energy transfer. Warm hands are touching cold ice right up in here. Molecules of in the hand are moving quickly, just like we've said before, because it's warmer than the ice. Molecules in the ice are moving slowly. So when the fast molecules of the hand hit the slow molecules of the ice, it speeds up the slow molecules of the ice, and in speeding up those molecules, it is heating it up. Ice increases the temperature, and the ice is going to melt. If you have a room temperature hand touching a room temperature glass, you don't have any heat transfer because the molecules of the hand are moving at the same rate of the molecules of the glass. So you don't have any change or influence of the molecules of the glass. They're at the same temperature. Now, one important concept. Whenever you have a transfer of energy, it is always from heat to cold, from hot to cold. I should put hot right here. From hot to cold. So the transfer of energy always moves hot. Now sure, if you have this ice here, your hand is going to feel cold. But what you're feeling is the absence of heat. I know this is kind of heady, but you're not feeling the cold spread. The cold is not spreading. It's the heat coming out of your hand. This is why you feel cold. Every time you have a transfer of energy, it's from hot to cold. Now, think about this. If you have the molecules that are hot and the molecules that are cold, the molecules that are hot can speed up the molecules that are cold. But how can these cold molecules slow down these hot molecules? And that's kind of where that comes in, because scientists are saying that you cannot have transfer from cold to hot. You just have an absence of heat there. Cold does not transfer. Okay, hope you've learned a little bit about temperature.